Good morning to everyone. So, I welcome you all to our channel, that is Effective and Efficient Electronics for Excellence, through which we are presenting the subject point of view conceptual and subject wise very important concepts of various subjects, in which we are discussing about the control system subject, in which we are studying now about the mechanical translational systems related topic. So this is the lecture number 46. This is lecture number 46. Here also we will see one more example on analogous system, that is nothing but for the given mechanical system. This is the example given. This is the block diagram, actually mechanical translational, in which you have basically one block is given like this. This you can call as your M1, and it is connected with two mechanical elements called as, one is spring constant, it is K1, and this is your B, okay, and which is connected to another mechanical block. This is M2. This is connected with spring constant K2. Okay, here the corresponding displacement is given as Y1, and here the displacement is given as Y2. On this block you have force F of t. This is force, applied force F of t, for which you write the differential equations and then draw the electrical equivalent circuit using force voltage as well as force current analogies. Okay, write the differential equations, that is the question. Write the differential equations. Write the differential equations, that is first question. And the second one is using force voltage analogy, draw electrical equivalent circuit, and also using your force current analogy Fi, draw corresponding electrical equivalent circuit. Same, that's what the question is here. Okay, so what could be the differential equation for this? What could be the differential equation? How many blocks are there in this? How many blocks are there? Mechanical blocks. Basically, we have two blocks basically. Therefore, by simply observing this, you can say that this is block 1 and this is block 2. Therefore, the solution part I am writing here, the solution part. So, the differential equation with respect to y1. So, with respect to y1 is nothing but with respect to m1 obviously. So, what are the elements that are acting on this? So, with respect to m1, the opposing force is there with respect to m1, opposing force due to mass element, opposing force due to your k1, as well as opposing force due to k2, because k2 also we have to consider. Therefore, if I write the differential equation with respect to m1, you can write the differential equation In short, I will write the differential equation with respect to y1, let us say. Here y1 is given. Then what you can write? It is m1 into d square y1 by dt square, clear, plus k1 into y1, this k1 into y1, clear, plus what else is there? It is k2. It is k2 into, what is that? If you take k2, y1 minus y2, y1 minus y2, and then b is also there, plus b into d by dt of your y1, equal to f of t. Call it as equation number 1. This is what the differential equation with respect to your m1. So the first element is the opposing force due to mass element. Second one is opposing force due to spring constant k1. This is the opposing force due to your common element k2, and b into dy1 by dt, opposing force due to this frictional coefficient. So all these are the opposing forces is equal to sum of opposing forces equal to applying force. This was the differential equation. Right. Similarly, the differential equation with respect to m2, next step, the differential equation with respect to m2. Okay, what will be the answer? m2 into d square y2 by dt square, this, and common element, that is k2 into y2 minus y1 equal to 0, because there is no force applied on this, only sum of opposing forces you must write. Equation number 2. These are called differential equations. This is the differential equation with respect to m1. This is the differential equation with respect to m2. Clear? Now what we need to find out? The electrical equivalent circuit. Okay, using our force voltage analogy. So I will remove this. Actually, I will erase this diagram because it is not required now, because we have noted down the corresponding differential equations. Therefore, we can now erase this. Clear? Now, so I already explained in detail in last presentation and even in previous presentation in force voltage. Now, using force voltage analogy, using your force voltage analogy. Now tell me. So equation 1 becomes from equation 1. So it is L1 into M1 is nothing but your L1. Then what is dy1 by dt? This is nothing but di1 by dt. Clear? I will remember, no? Because x equal to m1 corresponds to L in force voltage, and y1 nothing but various in previous example you have considered as x1, displacement is x, but here in this problem y. Therefore, y is equal to q. Then dy by dt is equal to dq by. So here y is nothing but y1. So y1 is equal to q1. dy1 by dt is equal to dq1 by nothing but finally i1. That's what. And k1 is equal to what? K1 is equal to 1 by C1. What is y1 then? What is y1? Integral of i1 dt plus what is k2? That is 1 by C2. It is integral of what is that? I1 minus I2. Okay, y1 minus I2 into dt, this particular, plus b also there. B is nothing but your r. R is equal to I1. R into I1 equal to your V of t. This is equation number 3 now. If you apply the force voltage, so M is equal to L. This is di1 by dt. It is 1 by C, and corresponding. This is nothing but we know that this is force. In force voltage, we must write the equation in such a way that V is equal to I into R form. All these are the voltage equivalents. voltage values actually, voltage across capacitor, voltage across inductor, voltage across capacitor, okay, and then this is the voltage across resistor, and finally voltage V is equal to IR form actually, I into R, like that. Clear? And this is from equation 1. Similarly from equation 2, it is L2 di2 by dt, clear, plus K2 nothing but 1 by C2 integral of what is this, I2 minus I1 into dt. Clear? Now from this equation 3 and 4 you can draw the electrical equivalent circuit. From these two equations you can draw the electrical equivalent circuit. So the electrical equivalent becomes like this. From these two equations you can draw both actually, force voltage as well as correspondingly. So from this obviously you can say that here voltage is input, two loops are there. In this loop currents basically we have to consider. Okay, in loops form you will have V of t is the voltage, L1 is the inductance, this is capacitance, this is the resistance. Is it not? What you will have here, you know, R means your resistance, nothing but what is it? Only R only. L1 is there. This is L1. This is also C1. This is also C1. What is the common element then? 1 by C2 is the common, means nothing but you will have something C2. This is C2. Clear? Finish. This is RLC. This is common element comes like this. Now, if you close the circuit now, you will have your V of t is like this. This is what your V of t plus, for example. And then this is what I1, and in this loop the current is your I1. Whatever the I1 we are mentioning, no, that I1 comes here, flows in this loop. And similarly if you consider the second, you will have L2 only. L2, this is L2 and then common element, and here you will have I2. That's it. Therefore L2 di2 by dt. So if you apply loop, if you write voltage equation according to Ohm's law, therefore it is voltage is 0 here, therefore 0 is there. This is equal to 0, no? So equation number 2, L2 plus I2, and this is equal to 0. This is equal to 0. This is equal to 0. Therefore voltage value is 0. Here voltage V of t is there for this expression. For here voltage equal to 0. Therefore no voltage is applied here. There is no voltage available. Therefore 0. L2 into di2 by dt. C2 is common. What is the I2 minus I1? So if you equate, that is equivalent to this. This is what your electrical equivalent in force voltage analogy. Similarly you can try on your own for that electrical, force current analogy. That is nothing but simply you will have all these are parallel combination. Instead of V of t you will have your I of t, and then if you all these RLCs comes in parallel basically like that, and all these elements comes in parallel. Let us you try on your own, and I will explain you the same in the subsequent our presentation. Clear? So with this I will finish off this presentation, and we will continue the rest part of it in the next presentation. Okay, thank you. Have a beautiful day.